on earth can this unremarkable hunk of rock cause this colossal explosion? This is the heart of the nuclear bomb, uranium ore. Gray, heavy, and practically useless. 99% useless, in fact. But take a few kilograms of that other 1%, just about the size of your standard grapefruit, and you'll have enough to unleash a force of destruction so powerful it can decimate an entire metropolitan city. So how do you turn this otherwise ordinary, sometimes colorful chunk of earth into a weapon powerful enough to erase a city in seconds? The process is extremely complex and involves highly specialized equipment and intricate scientific methods that must be repeated thousands of times with total precision. And it all began in the 1940s, when nations sought to dominate the planet by seizing control of one of its smallest building blocks, the atom. Today, the steps remain shockingly similar: mining, refining, enriching, compressing, and assembling until stone becomes fire and a small boulder becomes the bomb. Each stage is a study in scale, secrecy, and consequence, and every one of them leaves fingerprints on history. The bomb's story starts deep underground. Uranium ore is blasted from rock, drilled from open pits, or leached from sandstone deposits. It's then hauled to processing plants where it's crushed, treated with chemicals, and refined into a bright yellow powder called yellow cake. It looks harmless, almost like turmeric or chalk dust, but it contains the raw ingredients for either nuclear energy or nuclear fire. But here's a catch. In natural uranium, only 0.7% is uranium-235, the isotope that can sustain a chain reaction. The rest is uranium-238, which is far more stable. Therefore, yellow cake on its own won't work. It must be enriched. Enrichment is one of the most demanding industrial feats ever achieved. Yellow cake is converted into uranium hexafluoride gas, then pumped into centrifuges, tall, narrow cylinders spinning at supersonic speeds. The goal? To separate uranium-235, ever so slightly lighter, from uranium-238. One centrifuge does almost nothing. But when thousands are connected in cascades, rows of machines feeding one another, the effect compounds. Therefore, after endless spinning, the gas that emerges can be enriched to higher and higher concentrations of uranium-235. For nuclear power plants, only 3 to 5% enrichment is needed. For weapons, the bar is about 90%. The scale is staggering. It can take tons of ore, entire halls filled with tens of thousands of centrifuges, and colossal amounts of electricity to make enough fissile material for a single bomb. During the Manhattan Project, enrichment plants in Oak Ridge, Tennessee covered more floor space than some cities. Thousands of workers clocked in daily, never knowing the true purpose of the strange new machines they tended. Uranium wasn't the only option. Scientists discovered that uranium-238, when bombarded with neutrons inside a reactor, could transform into plutonium-239, a new element, man-made, dense, and explosively potent. This path promised a faster, more abundant way to fuel bombs, especially when enriched uranium was scarce. But plutonium had never been seen in usable quantities before reactors. Therefore, the Manhattan Project built massive secret facilities in Hanford, Washington. Reactors produced plutonium, and vast chemical plants separated it from irradiated fuel rods. Entire towns sprung up almost overnight to house the workers, most of whom never knew what they were truly building. Plutonium offered abundance, but it came with a fatal flaw. A simple gun-type bomb would make plutonium pre-detonate, triggering a weak explosion before full yield could be reached. Therefore, scientists had to invent a completely new approach: implosion. Implosion meant surrounding the plutonium core with carefully arranged high explosives. When detonated, these charges had to fire within millionths of a second of each other, creating shock waves that crushed the core into a supercritical state. This demanded explosive lenses, ingenious charges shaped to bend and focus shock waves like glass bends light. The challenge was brutal. Miss the timing by a microsecond and the weapon fizzles, but succeed and the yield multiplies dramatically. At Los Alamos, scientists set up firing ranges, high-speed cameras, and electrical oscilloscopes to measure detonator precision. They blew up hundreds of test charges to perfect the timing. It was a race against time, secrecy, and fear. On July 16, 1945, in the desert of New Mexico, the gamble was tested. Scientists crouched in bunkers, waiting for history to change. At 5:29 a.m., the plutonium implosion bomb, nicknamed the Gadget, detonated. The blast turned sand into glass, lit the sky brighter than dawn, and launched a mushroom cloud 40,000 feet high. Shockwaves shattered windows 100 miles away. Oppenheimer recalled a line from Hindu scripture, "Now I am become death, the destroyer of worlds." Therefore, weeks later, uranium was used in combat. On August 6, 1945, the bomb, nicknamed Little Boy, fell on Hiroshima. Its design was simpler. Two subcritical pieces of enriched uranium slammed together. The explosion leveled the city. Tens of thousands died instantly. But uranium enrichment was so difficult that only one bomb was ready. Therefore, the second strike used plutonium. On August 9, 1945, Fat Man detonated over Nagasaki. The implosion design worked exactly as intended. The devastation was immense. The nuclear age had begun, and every weapon since carries the DNA of these first three devices. Modern nuclear bombs are more advanced, but the fundamentals remain. The fissile material, uranium or plutonium, is machined into precise shapes. Fractions of a millimeter matter. Even tiny flaws can cause a dud. Therefore, machining happens in specialized facilities with robotic arms, laser measuring devices, and multiple quality checks. Once the core is ready, it's surrounded by layers, conventional explosives, neutron initiators, reflectors, and safing mechanisms. Assembly is compartmentalized, so no one team ever sees the entire bomb. But secrecy is also safety. It prevents mistakes and enforces redundancy. In many nations, the two-man rule requires two authorized people at every critical step. In the early Cold War, testing meant hundreds of detonations in deserts and oceans. But fallout spread across the world, causing outrage and health crises. Therefore, testing moved underground and later into laboratories. Today, supercomputers simulate explosions, hydrodynamic labs mimic implosions, and subcritical tests study nuclear reactions without triggering a full chain reaction. The process is quieter, but the destructive potential is greater than ever. So, how are nuclear bombs made? By mining ore, enriching uranium, breeding plutonium, machining cores, and surrounding them with explosive precision. Each step is technical, industrial, and exacting. But the outcome is brutally simple. Unleash energy millions of times stronger than chemical blasts. 9 nations still possess them. Thousands remain deployed, and every stage of their creation, or enrichment implosion, still carries the weight of 1945. That dull gray sphere we started with isn't just metal, it's history condensed, politics crystallized, and science weaponized. And it leaves one truth that cannot be undone. Once humanity learned to split the atom, it could never go back.